Live stream is good. Yeah, check the room. But okay, so option B.
So Onur is going to talk to this.
You wait. Just speak.
But
No, I will change it. Just change it.
No, yes.
Simple.
63.
Huh? Say it again.
63.
63. Okay. We have 63 people registered for this course, but I don't, even though I don't have to count, I don't see 63 people here. So what's going on?
Okay, the issue is the problem is with the switch. And
Okay.
we have problems with probably with multicast,
Okay.
which is coming it from another room. I can't fix it within minutes. Right?
Okay. When do you think it can be fixed?
I need to check when the room is available.
Okay.
Do you have any? Could you fix it, or could you do the Zoom in another way?
Yes.
Yeah, we have our own setup. Yes. Yeah.
Okay, good.
Yeah. We'll use our setup.
Until when?
Say it again.
Today.
Today until 4. Yes. Until 4.
Until 4.
Yes. Yeah.
Right.
If you can fix it after that, we'll have it next week right here.
No. As soon as possible.
Okay. Thank you. Okay. Is everything online okay? Like live stream, etc. Okay. And you can hear me online with this microphone?
Yes.
Okay, it's all good. Yeah. Okay, thank you very much.
We'll fix it as soon as possible.
Okay, thank you. See, this is a fundamental principle. If you have one processing system that doesn't work, have another processing system that works. It's called dual modular redundancy in dependable computing. You have redundancy in systems, and if one doesn't work, you use the other one. It's also like a hot spare, basically. It's a spare system that can be swapped in live right away, and I can continue to operate. Existing systems are really not like that if you look at the processors. Yeah, I could teach a course on dependable computing, but we're going to focus on computer architecture today. Anyway, we're not terribly late, I guess. What time is it? Okay, 2 minutes. That's not bad. So hopefully everybody's here for computer architecture. Is that true? Okay, that's great. I see some familiar faces who have taken our previous courses, which I'm going to mention early on. Some things will be similar to what you've seen, but then we're going to diverge later on. So there's certainly some overlap in the courses. But I should mention to begin with that this is not a basic course. This is a master's level course. Some seniors also take it. PhD students take it. This is really an advanced course. So if your goal is to learn about how a processor exactly works, I will refer you to materials later. Our goal is to really do something else here, to cover cutting edge while focusing on some fundamental issues in the cutting edge design of computing systems, computer architectures. Does that sound good to everyone? Okay. Just to make sure you're here for the first course, so you should get what you expect. Okay, let me start, I think. How many people are here taking the course? You can raise your hand. Okay, that's good. How many people are computer science students? Or data science, computer science, let's say. Okay, how many people are electrical engineering? Okay, that's good. We have a good mix. How many people are none of those? Which is also fine. Okay, that's fine. Yeah, I know. Yeah, some people are TAs also. I can recognize the TAs more than all the students, except if you have not taken my course, of course, previously. Okay, we're going to talk about computer architecture, and we're going to cover CS, EE. So this course spans across the stack, basically, both hardware and software. We're going to start with a lot of hardware, but then we'll move to software later on as well. Let me just introduce myself quickly and the major teaching folks. This is myself, as you can see. I broke my ankle 2 months ago, so now I'm standing, which is good. If this course was like 1 month ago, starting 1 month ago, I would be sitting, which wouldn't be very convenient here, as you can see. I could sit over here, but now I can stand at least. That's the good part. But that's another example of robustness. Like something breaks, you will actually figure out the importance of robustness when something breaks. So don't take it for granted. When you design systems, make it robust, make it work. I'm actually very worried about our future, robust future going into the future. I fly a lot, and I'm not sure if we're doing due diligence to designing our systems to be safe and robust going into the future. And people are talking about self-driving cars. People are talking about going into the space, and our computers are not robust enough. I don't think we can tolerate that. We'll be dying by the masses, let's say, if these things actually scale up, scale up into the future as they're designed today. So I think we should be much more careful in the design of computing going into the future. Okay, so I've been here for almost 10 years now, 9.5 years, both in computer science and electrical engineering more recently. Before this, I was at Carnegie Mellon University. I was a professor there. I spent some time there building the computer architecture program, and you're going to see some of the works that we've done related to that. Before that, I was at Microsoft Research. I started the computer architecture group where we did a lot of studies on many interesting things. You may again see some of those things. And before that, I was at University of Texas at Austin, where I got my PhD. How many people are PhD students here? Okay, there are some people who are taking PhD. You're not a PhD student anymore. Okay, I know you. Okay, he still thinks he's a PhD student, maybe recently graduated. I think that's a good mindset, actually. You're always a student. That's my mindset, at least. I think this course, in my opinion, this course would provide much more important things about mindset than anything else. Like, I think my mindset is you're always a student. And if you're always a student, even though you're a professor, doesn't matter. You learn a lot, basically, and you can always innovate. Right? That's a very good mindset to be in. You're always a student in life, essentially. Okay, before I got my PhD, I was in probably many of your shoes doing masters and bachelors. I did my master's actually at Texas, but my bachelor's was in computer engineering and psychology at the University of Michigan, where I got exposed to computer architecture in my first year from a person who was a passionate teacher, Yale Pat, who went on to become my PhD advisor. So I studied under him for a long time, let's say, at least 8 years. And I still study under him. We may talk about what he has done later on. Okay, before that, I was a high school student in Turkey. Okay, this is my email address. That's the website, so you can now find a lot of information. Feel free to email me. If you don't get an answer, feel free to email me again. There are robustness issues also, and both receiving email and reading email and keeping up with email. There's just too much going on, basically. So robustness is really fundamental to everything we do. It's really the beginning of everything, I would say. I should also say that maybe I'm not a very regular academic. I actually worked a lot in industry, and I actually cherish working with industry, even though I don't cherish doing immediate things that the industry does. I cherish working with industry to understand the problems that they have, and problems that they may not be thinking about, but they should be thinking about if they want to do something big 10 years down the road, 5 years down the road, maybe 20 years down the road. So I worked, for example, during my PhD studies, I was at Intel and AMD. I did 5 summers of internships there, both learning and also implementing some of the ideas that I developed in my PhD thesis on their processors. And after that, I started the Microsoft Research Computer Architecture Group. I also spent a lot of time at Google, VMware, Microsoft, and some places who shall remain nameless for now. Yeah, and I was on sabbatical at Stanford how long has it been? I guess it's already been more than a year. Yeah. Okay, that's in a nutshell me. Hopefully I'll get to learn you also. But you're here because I'm teaching the computer architecture course, and we do a lot of work on computer architecture. I'm very passionate about research, teaching, education in architecture, systems, hardware security, bioinformatics. And these are some list of topics that we do a lot of research on that I'm not going to cover right now, but you will see a lot of these topics coming up in this course and other courses. I should say that we do a lot of work on fundamental topics, but fundamental topics actually need to evolve into the future to essentially build the cutting edge. So what we're really interested in my group is really how do we think the fundamental system design such that we can be much more energy efficient. Our goal is not to, let's say, design the next processor that's a little bit energy efficient compared to the last year, right? I think that's frankly a bit boring for me because my goal is to do something bigger, right? 10 years down the road, how should the processors be designed so that you can be fundamentally much more energy efficient? How do you change the paradigm so that it's much more fundamentally efficient, right? So we're going to deconstruct a lot of things in computer architecture today, which is very processor-centric. We're going to look, in fact, we're going to start with memory and storage because that's the major bottleneck today. So I'm going to talk a lot about memory and storage today. Does that make sense? So if this jives with you, if your mindset is this way, if you want to be a critical thinker, you would enjoy this course a lot. If your goal is to figure out how should you design the next processor, it's not going to work very well. Let me put it that way. That's a different course that I teach, but not this semester. And I don't want to teach the same course every time because that's kind of very boring, right? I want to teach different types of courses also. Okay. Okay, we have a co-instructor. My co-instructor is Mohammed Sadr. He's sitting over there. He's going to be giving some of the lectures also. In fact, some other people also will be giving lectures. But Mohammed has been working with us for a long time now. He started in 2017 when he was a PhD student, visiting PhD student. And he's right now a senior researcher and lecturer in my group. He's gotten all his degrees in one of the most respectable universities in Iran and the world, Sharif University of Technology. World is important, that's true. And you can contact them in this email address. Some people think Iran is not part of the world. We're not like that. And you may know who those people may be, right? The whole world is the same, essentially. There's no difference between people. I travel a lot, and there's absolutely no difference between people, except we like creating differences. Okay, there are a bunch of research and teaching areas that overlaps with what I do, certainly. And he's going to give some of the topics in this lecture. And we have, he should be a co-instructor maybe next time we teach this course, but our head teaching assistant right now, at least technically, Konstantina, who's sitting over there. And she is a senior lecturer, research and lecturer also with Safari. When did you join? 2023? 24, okay. She's been with us for 2 years. I was on his PhD thesis committee and I gave her a hard time. So she decided she didn't have enough hard time in her thesis committee. So she wants to have even harder time in my group. That's a joke, of course, but apparently she's not having enough hard time. So she's still with us. Yeah, she's going to be teaching some of the lectures as well. And she's going to be responsible for a lot of the organization of the course, TAs. So if you have complaints about the labs, etc., you can go to her. Don't come to me. I'm just kidding. You can come to me also, but she'll be more accessible in general. And she's definitely nicer than me. No question about that, you know. Okay. I'm going to make a lot of jokes here. That's okay. And then you will see a lot of teaching assistants. I'm going to introduce them probably in the next lecture tomorrow. This is a course really. So we care a lot about research and teaching. Our culture is that way. And I'm going to describe you why that is the case. So this particular lecture will be a lot about mindset and a little bit about basics. So this is my research group in 2020. And our goal is to actually really deliver the best lectures possible as far as we can. So a lot of people in my group are involved in the lectures. There'll be TAs, there'll be people who will interact with you in the labs, so you can ask them questions. And you can see some more about them. So if you're interested, you can learn a lot about us online. These are some of the newsletters that we have put up online. So there's a lot of information. My goal is not to overload you with information over here, but just to give you the slide. So if you're interested in learning about people who are teaching the course, you can learn a lot. Does that make sense? And we have another edition coming up for the newsletter. And there's a lot more information online that you may see, which I'm not going to cover. So our main goal as a research group is both research and teaching. But research is extremely important. This is an incomplete list of, well, complete list of PhD alumni, but incomplete list of postdoc alumni over here. And some folks over here may be giving lectures also if they're in town, let's say. And some of them may be in town. And you can see that this list is growing. So we're proud of the education that we deliver for both researchers as well as people who want to get degrees, let's say. Okay. And I cannot keep up with Girai's awards, so it's very hard to. These are the awards that he received for his PhD thesis. He received at least 3 major dissertation awards from 3 different communities. And we're going to cover some of the work he has done in this lecture. Okay, you can find a lot more information about me and our thoughts online also. And if you're interested in doing research, certainly you're in the right place in computer architecture, because we always are looking for good people from across the world. But here you have kind of a special let's say, advantage, because we can talk with you much more easily than we can talk with someone who's far away in the world, right? So if you're interested in doing research, you can certainly talk to us. Okay, let me give you some idea on what this course is about and what we would like to do. Because in my opinion, this course, being an advanced course, is very much aligned with what we would like to do in research. Our goal is to really enable fundamentally better computers. For this, we would really like to understand the limitations of existing computers. And we want to look at how to move into the future, right? Today is actually very interesting because there's a lot going on in computer architecture. Like we have a lot of processors and different accelerators tailored for different things like machine learning, accelerating video, accelerating speech recognition, etc., vision, genomics, biological signal processing. So these accelerators are there, and they're multiplying essentially. We're trying to specialize computation and communication to the patterns that different workloads have. And memory is a big bottleneck, so people are actually experimenting with a lot of interesting things in processing inside the memory. But the system is actually bigger than that. There's storage, sensors, interconnects, and these all can have processing capabilities. So I think it's good to think about the system this way. So if you look at, for example, traditional computer architecture course, most of it is really focused on processors, right? That's not my goal over here. My goal is to really change the thing here. We are going to focus a lot on memory and a lot on interconnects and some on processing also, parallelism, but that will come toward the end of the course, toward the last third. If you want to focus on processors, that's digital design and computer architecture, the fundamentals of computer architecture. I'm going to talk about that. So these are some of the topics that we cover in my group, and that also we will cover in this course, not in this order necessarily. But I think there are a lot of issues that we need to solve, and I'm going to motivate this later today also. We want to design fundamentally robust architectures, reliable, secure, safe, available. We had an issue with reliability, availability at the beginning, right? It could be exploited for security, safety as well. We don't know that here. This is not a safety critical situation, but if it happened in a safety critical situation, then this would be fatal potentially, right? Fundamentally energy efficient architectures, we're going to talk a lot about energy because that's one of the major limiters to computation today. Low latency and predictability, we're going to talk a lot about that later in lectures. And one of the things that is actually quite important today in the cutting edge is how do you use machine learning or AI to help with the design of the architecture and the system? How do you design controllers that can do better decisions, for example, inside a processor, inside the memory system, so that you can be much more accurate in prefetching data, getting data from the memory, for example. So we're going to look at that. And there's a lot of opportunity there going into the future. And the flip side of it is actually designing architectures for machine learning, AI, and different domains, genomics, medicine, and health. We're not going to cover everything, of course, but we're going to give you a sampling of different things in these areas. And these are very fundamental topics in the end. And hopefully, part of my goal with this course is, hopefully you'll get excited and inspired about some parts. And some of you may actually go to industry and do great things to fix our computing systems for the future. Some of you may go become software engineers or AI engineers, and you would be aware of what's going on in computer architecture, and you can actually do things in a much better way. Some of you may become researchers, some fraction of you, probably a small fraction in general, that's what happens. And you're equipped with actually designing much better systems, right? So there are a lot of potential possibilities. And some of you may become businessmen or businesswomen, and in the end you decide, oh, I know about computer architecture and I can do a better business this way, right? So hopefully some of the things that you learn in this course would be useful regardless of whatever path you take. Okay, so this is the transformation hierarchy. If you took DDCA or FOCA, which I'm going to introduce soon, you would have seen this multiple times. I don't know why this thing is not working. I don't see the pointer. Do you know why that is? Or do you see it? Okay, nobody sees it. Okay, anyway, it's not that important. I want to point to something, but maybe I'll point this way. Okay, there you go. So basically, we want to solve problems, and I'm going to get to that later today. And we want to solve problems using electrons today. Unfortunately, we cannot communicate with electrons. Humans have not discovered how to communicate with electrons yet. It's good to think about this because this is actually a real problem, right? We can communicate only with humans, barely. We have actually a lot of communication problems, I think, in the world. But ideally, we would like to communicate with the electrons, right? And we want to say, electrons, go do this for me, right? If life was that easy, we would have done a whole lot better in computation. Instead, we built this transformation hierarchy that is very inefficient if you think about it, because we cannot communicate with the electrons. We transform the problem to an algorithm to a language, and then we execute on system software. It goes through an interface, and then at the hardware levels, the green ones, a microarchitecture is designed, which is implemented in logic, which is implemented using devices, which operate based on the physical principles of electrons, right? So I think what I would like to get to you is really this course, in my opinion, what I would like to communicate is thinking about the world differently, right? I'm not sure if people think about the world this way in other courses, but I think about it a lot of the time. If I have a way of communicating the problem with electrons, maybe possible, I don't know. Maybe AI will at some point will figure that out over time if people actually think about it the right way. Then I could be much more efficient in my systems, right? Today I have to go through all of these layers of software and hardware. Think about it, yeah. That's why I think if you don't get anything out of this course, hopefully you get out some mindset about thinking differently. Okay, so computer architecture, narrow view is more hardware-software interface and microarchitecture, and you've seen it in probably earlier courses. In this course, we're going to take a more broader view of architecture, which is really algorithms to devices. We're still going to be focused a lot on the middle, but today you cannot do a whole lot if you just optimize the middle, essentially. Basically, if you want to get the highest efficiency, performance, robustness, security, you really need to consider the entire computing system across the stack. You may want to, for example, co-design the algorithms such that it matches the devices and the microarchitecture. Machine learning accelerators, for example. Design a matrix multiplication mechanism. That's an algorithm. There are many algorithms for doing matrix multiplication. Figure out which one matches the underlying hardware and change the underlying hardware such that it matches your algorithm in a nice way. Right? That hardware could be analog hardware that can do analog computation. That hardware could be a traditional CPU, GPU, FPGA. Then you need to really co-design your algorithm with the underlying hardware. And again, you need to think about the interface or whatever lies in between, assuming you want to go through this, let's say, transformation hierarchy. And this is what's happening actually today in industry also. We want to specialize as much as possible so that we can get the highest efficiency and performance. And that's kind of what we're going to see in this course in many different directions. Not every lecture will be about this, of course, but this is kind of the mindset. Does that make sense? So if you look at, for example, one of my favorite examples, Google TPU, the tensor processing unit. It's essentially a systolic array architecture. And this architecture is designed in a way such that matrix multiplication is very efficient. Right? It's a specialized architecture for matrix multiplication. If you want to do database acceleration on this, good luck. Well, you can try, but it's not designed such that it's catering for the primitives of database acceleration at the high level. Okay, we're going to see more and more of this later on. Okay, this slide is interesting, but this slide, if you're interested in learning more, this was actually published 2 days ago, or maybe yesterday. What's the date today? Okay, 2 days ago. If you're interested, you can take a look at this. I'm going to mention this later on also, yeah. Okay, I already said this, but in a different way. I'm going to give you some perspective first in this lecture. Why are we doing what we're doing? Because I think that's really important. This is actually something that's missing in the university culture. Maybe if you think about it, I'm a very old type of professor. I may not look like it, but I think there were universities in ancient Greece, for example. We have a lot of Greek people here. They may know about it. Part of Turkey used to be ancient Greece also. So I visited some of these sites where Aristotle taught, for example. And these guys were actually doing the right thing in really teaching people. They were actually questioning the fundamentals, right? They were not going to the board and always writing, okay, this is how you prove some theorem. This is how you exactly design a processor. They were getting to the core of a university, which is really asking questions, critically analyzing things. Right? And I think universities have kind of strayed away from that a lot over decades. It's become more of a, let's say, creating soldiers for industry. Right? Even right now, I'm questioning, as you can see, right, how industry, how university operates. So basically, if your goal is to learn exactly how a processor is designed, this is not going to be the course. If your goal is to learn how to question things, you're going to question everything, hopefully, in this course. Right? And if you don't like it, go and visit Pergamon in modern Turkey, ancient Greece, and see how Aristotle taught people. Assos also, actually. Yeah. No, do you know about Aristotle? Something? You learn about him? Okay, good. Yeah, he lived in many places, but yeah. Okay, so that's my basically point over here. Our goal is to really communicate something bigger than what is done today, because that bigger thing is what's really needed, in my opinion, going into the future. At a university, we want to educate people who think big, who are really trying to do the right things, and who are really always critically thinking, are we doing the right thing? Are we doing the right thing? Are we doing the right thing? And right thing, of course, depends on the trade-offs, etc., and the application space if in computing, for example. So our goal is, that's why I want to give the mindset to begin with. Okay, so basically, in a university, teaching and research, in a research university especially, teaching and research are always coupled, in my opinion. Sometimes research universities don't think about teaching as much, but I care a lot about teaching, and I have a different style, as you can probably see. But essentially, I think these are two sides of the same coin. In research, your goal is to discover something new. Ideally, no one has discovered, right? That should also be the bar for research. If you look at current research, most of it is not like that. People are trying to do tweaking of the existing thing, and fundamental innovation is relatively low. Again, I'm critically thinking, as you can see, right? Real research is discovering something that no one has discovered before. That moves the needle, right? Maybe not immediately, maybe 30 years down the road, it actually has impact, but it moves the needle. Now, once you discover that thing, that becomes the domain of education, because it's discovered, it's known, at least to some level it's understood, it can be taught, right? So research, you discover something, you educate the community, and it becomes well-known knowledge, and then that becomes part of the teaching domain, and you can teach it. Because now, what does teaching mean? There's a known domain that's discovered, and you tell it to people so that they learn about it, right? That's the idea of teaching, essentially. Essentially, you're doing the same thing in research and teaching, except basically you're educating the community, except in research, you're educating the community with something that only you know, because you have discovered it. And then once you educate the community, everybody knows it, and everybody should be able to teach it. Right? So that's the distinction. But these things are very important together because they drive each other, right? How do you actually do new innovation? You actually go and get education, teaching, and you learn about some concept. You learn about how to destroy it critically, meaning think critically about it so that you find issues with it. And once you think critically, you can actually do research, right? You can actually change. You can actually discover something new. Okay, so that's the idea. And we keep doing this loop where we teach, where we do research. And that's why you see in a lot of our courses, we critically think about things, question different approaches, and also talk about cutting edge things that people have discovered recently. So we're going to talk a lot about cutting edge things in computer architecture in this course. Does that sound good? Interesting? Okay. Okay, not the boring processors. Not that I have anything against processors, but go and take DDCA, Digital Design and Computer Architecture, and FOCA. You can ask him, since he apparently liked FOCA. He's back in computer architecture over here. That's where we cover the processor design. Okay, so we have a lot of courses. So now let me introduce some of these courses, some of these terms that I've been throwing at you. You can find all of our courses online. We try to be as structured as possible on these things. They're all on YouTube also. They're all live streamed. This is also live streamed. It's still live streamed, right? Okay, good. So if there are questions online, we take it. We tend to take a global approach to education. Okay, these are our major courses and lectures. so this is digital design and computer architecture. How many people took the DCA here? No one. Okay. Those guys suffered a lot, so they don't come. So DDCA is the freshman course. And it's a computer science course, but I wish really more EE students took it so that they get exposed to these concepts immediately at the freshman level, frankly. But yeah, that's a different discussion. Essentially, that's where we cover a lot of execution models and processor design. FOCA is something that we introduced because of this gap in EE, where not a lot of people get exposed to computer architecture early enough. And this is a junior, senior level course. How many people took that one? Okay. We have one person who defected that. Maybe online. Since there are 60 people registered, I cannot really sample well over here. But yeah. And then you're here for the advanced computer architecture, which is what we're here for. And then we have a seminar in computer architecture, which you also took, actually. How many people took seminar in computer architecture before? How many people are registered for it? Sometimes people do it together because seminar is completely different, where we actually cover research papers. So if you want basic materials, how a processor is built up from transistors, this is the course to take, DDCA. We cover a lot of execution models, GPUs, systolic arrays, etc. And then we also go to memory at the end of this course. This digital design, computer architecture, and a little bit of memories. FOCA is a somewhere in between course, basically. FOCA is somewhere in between DDCA and this course. There are some topics that are covered in DDCA. So we actually still build a processor over here. You learn about the fundamentals of microprocessors. But then we also cover some research topics in fundamentals of computer architecture. So it's kind of an intermediate course. Whereas this course is much more advanced, called ACA. And here we actually talk a lot about both the cutting edge and what are the fundamental issues that we have in the field and how can we actually try to solve them. Labs are a little bit, unfortunately, we need to revamp the labs at some point so that they're actually also more research oriented. But labs here are going to be more similar to FOCA in the sense that you'll design some caches, multiprocessors, etc. But we need to revamp the labs given that FOCA is there now. So labs are going to be easier, in my opinion, than the concepts we're going to cover. But that's ease is in the eye of the beholder or doer, right? For me, it's easy. For you, it may not be easy because you'll need to debug all of those things. Okay, so these are some courses. And we have an extensive list of courses. So this was taught last time, fall 2024. You can go and look and see what you can expect. We're going to pretty much follow the same structure in 2025, that we followed in 2024. So you can see what you expect in the course. So take a look at that, I would say, if you're unsure about taking this course. And also, of course, we always update our courses every year. So there will be some new topics that we discuss. So these are some older versions of some of these courses that I'm going to skip over here. So seminar, very quickly, seminar is really about presenting papers. So we cover papers and every student presents a paper on computer architecture and critically analyzes the paper. And there is a group discussion after that. So that's a completely different type of course. The goal is to really enable you to understand, read a paper, critically analyze it, critically present it to an audience, and then drive a discussion so that people in the audience can discuss the paper. Okay, we also have some specialized courses that I'm going to skip, but if you're interested, you can find them online, especially processing in memory. We're going to cover some things, but if you really, so for example, if you really want to delve into RowHammer, DRAM, emerging memory systems, PIM, there are even more specialized courses that you can take, although some of them are not as up to date as this course is going to be, because as you can see, 2022, 2025, that's actually a long time. Okay, we have a course on genomics as well. I'm going to skip these. These are for your reference. If you're interested, you can click on them later on. So these are these specialized courses. We call them projects and seminar courses. A lot of them are hands-on courses also. You can do hands-on FPGA acceleration, for example, for genomics. But that's not the subject of this course. We also do a lot of education in the community. So we organize a lot of things online. I'm going to mention some of these later on, but this was a special session we organized in memory processing. This course, we're going to talk a lot about processing inside memories, which I'm going to introduce later today. And the next few lectures are going to be on that topic. But this is a paradigm that is going to come, in my opinion, and change the world in terms of energy efficiency and performance and security. So it's good for people to be exposed to it as soon as possible. And hopefully you're going to see why this is happening today. Okay, we have a lot of tutorials on this topic also. Again, these are material that I'm throwing at you that you can look if you're interested, or you can just ignore if you're not interested, right? And they may make more sense, actually, after we cover them. And when they make more sense, I'm going to throw them at you again. Okay, so these are some of the processing in memory tutorials that we have organized in recent years, including this year at major conferences, 2025. And in these tutorials, different people give both educational talks as well as research talks. So this is actually a great example of teaching and research going hand in hand. You educate the community about processing in memory, how to do processing inside memories. And there's also some research talks that are described that no one knows about. So that's good. Okay, any questions so far? We're still basics, so okay. We do a lot of open sourcing, and you're going to use some of these tools that we open source in our research group. I actually am a very big believer in open source that enables fast global progress in important issues. This is our GitHub, which you may actually become familiar with. We open source a lot of things. You can see there are 116 repositories right now, apparently. I cannot keep track of them. That's a lot. Yeah, but some of these tools that you're going to use in the labs are actually used in industry. For example, RAMulator 2 is used heavily in industry, many companies, major companies, as well as academics. So the goal is to model memory systems and to, there could be multiple goals actually, to figure out which kind of memory system you want to design at your processor. That's a short-term goal. Or what kind of memory system architecture you should design going into the future. So this tool is very flexible. So we do a lot of simulation tools. And there's also similar simulation tools that we have developed for SSDs and benchmark suites for processing in memory, for example, and also some FPGA-based infrastructures to test memory, to discover new issues. And we're going to talk about some of those issues in this course also, and maybe in this lecture in a little bit. Does that sound good? Yeah. So I think another mindset thing, open sourcing is actually very good, in my opinion, because it enables fast progress, right? You can, let's say, describe an idea, you can develop it, you can write a paper about it, but if you don't open source the artifacts, it's very difficult to, well, it is possible, but it's still difficult to get the impact of your idea to the entire world. If you open source the artifacts, it's open science. First of all, that's good. I think it follows the principles of open science, right? If you don't open source, it's not clear exactly what you did. Yes, you may be completely honest, but you may have made a mistake, right? Somewhere. If you open source, that mistake can be discovered by someone else, and you learn about it and you fix your mistake, right? I think that's very good. A lot of people, unfortunately, again, this is I'm going to do a critical analysis of academia, let's say. A lot of people, unfortunately, are afraid of admitting their mistakes. This is very human also, by the way. And as a result, they're very afraid of open sourcing their things. And then you basically get all of these papers that are not reproducible, etc. If you may have read papers about reproducibility crisis in science. Well, one of the reasons it's happening is people don't open source things carefully or well, right? There are other reasons, of course, but open sourcing is one of the reasons. Well, if you open source, then you can correct your mistake. We actually did it with a recent paper. There was a bug in our simulator in one of the papers that we wrote, and another paper used our open source repository, and we corrected that bug and updated our paper online. It didn't change our major conclusions. It just changed some of the numbers, but still, this is the right thing to do, right? So that's why open sourcing is very useful. That's one of the reasons. It keeps you honest. And our goal in doing science is finding the right thing, right? Doing the right thing, finding the truth. Our goal is not to publish papers. I think that's another critical thing that I will, again, stick to academia, let's say. There's too much focus on publishing papers in academia today. The goal should be doing the right thing, advancing science. And for that, I think open sourcing is really critical. Right? Okay, so that's one perspective. The other perspective is, of course, you open source, and then your ideas are available to everyone to actually use or evaluate, right? Which is good, because this is like crowdsourcing in a sense, right? You know the term crowdsourcing? You can solve one problem only by yourself and try to figure it out. But if you actually get help from a billion people, maybe the problem will be solved in a much better way, right? Everybody actually uses your source code to actually do something. Okay. Okay, in terms of publications, don't get me started on machine learning conferences. There's so much incremental publication in machine learning conferences that I think no one can keep up with that mess. Mess is a nice word. Okay. Okay, so we're going to actually talk about a lot of papers, talks, and artifacts, and you can find them, almost all of them online in one of these forms. Okay, let me cover some of the basic principles that we follow. I've been covering some basic principles, but I'm going to cover some more. Sorry. Maybe you didn't expect this to happen, but you're here. So now, okay, we've already talked about this. Teaching drives research, research drives teaching. I think our goal in both in research as well as in this course is going to be focused on insight. Like, what is the insightful thing that we actually find in this idea, for example? We're going to talk a lot about ideas. And I think that's the most important thing. Ideas are really important. Implementation comes always next, right? And we're going to talk about a lot of ideas in memory initially and many other things later. Implementation will be a secondary focus in general. But we're going to talk about, in some cases, we're going to talk about a lot of implementation issues as well, because implementation is really important also at some point. But ideas are, in a sense, a bigger thing, right? You come up with a big idea, and you can implement it in many different ways. You may not be able to know how to implement it today if you have a big idea, but 10 years down the road, somebody will figure out how to implement it because technology will evolve that way, right? You may not have the technology to implement your big idea. Right? Yeah. I think one of my examples over here is the Sydney Opera House. How many people know about the Sydney Opera House? No one? Okay, you know about it. You've seen pictures. How many people have been there? How many people are from Australia? I guess Australians are happy and comfortable in their continent. They don't want to come to Switzerland. And I understand that. I've been to Australia. But basically, Sydney Opera House, the architect of Sydney Opera House, envisioned something that was basically extremely difficult to build. His idea was having these curves in these walls. And if you've seen this, I cannot really, you have to see it, basically. And that thing was not implementable for many years. And then eventually, it was implemented, right? So it required a lot of work to implement this thing. So that was an idea. Idea was good, but it required implementation to actually really truly be good, right? And we're going to see some of those also later on. Actually, there's other examples of this in Stahlhofen, for example, an ETH alumnus built. I think there's a new thing over there in Stahlhofen. Have you guys seen it at the train station? The Calatrava built a new thing over there. Okay, you got to go see it. I didn't take a picture of it because of my foot. I haven't explored Stahlhofen as much recently. But Stahlhofen, the station was built by Calatrava, but now he has revamped it in 2025. So go and take a look. He had ideas that may not have been easily implementable. Easily implementable, what does that mean? You may not have the materials for it. You may not have the implementation knowledge for it. You may not have the technology for it. You may not have the money for it. In fact, Calatrava is known for asking a lot of money for the implementation of different things. Like the Oculus in the New York City. That's another beautiful building. I don't have a picture. I should have added these pictures. That's basically a train station, another, let's say, metro station. And that thing cost $4 billion in New York City. And Calatrava was asking for more money to implement. But then he didn't get it. So that train station that looks like a bird cannot move its wings now. It's just a bird without movable wings. Okay, for these to actually make sense, you need to imagine. I'm imagining these places in my head because I know the pictures. Unfortunately, we're not at a point in technology yet that when I imagine something and know the picture, you can also see it over here, right? What are these AI people doing? Why don't they just do it, right? This is the problem, basically, I see, right? This is the idea. My idea is I imagine something and you see it over here also. Should be doable. Not yet. Okay. Okay. Basically, I think we're going to focus a lot on learning and scholarship. That's really important. Hopefully, I gave you some examples of that earlier with taking a critical view on academia. I think a lot of academia has diverted from learning and scholarship, in my opinion. It's become more like publishing mills. I think we should be more careful about that. Our goal is really learning and scholarship. And again, if you want to have a litmus test, ask what Aristotle did. Yes, that's thousands of years ago, but those guys were trying to do something right. Okay, and I think in this classroom also, but also in my research group, we strive for an environment that values free exploration, everything else that I said before, as well as free exploration, because new ideas actually comes from free exploration. If you're constrained too much, you cannot develop any big idea, right? For example, if your constraints are, you have to have a processor-centric model, you have to have a 10-stage pipeline, you have to have memory as it is, you have to have cache as it is, what are you going to improve? You cannot move anywhere, right? You tweak things. But if your constraints are nothing, meaning this processor that someone designed, I can completely revamp it and design something else. That's free exploration right now, right? A lot of people are afraid of it. A lot of companies are afraid of it because they want to make money, business as usual in the next quarter. They want to satisfy their shareholders. Yes. In fact, they don't want to make money. They want to make money from shares. They don't want to make money out of products. So we're in a kind of messed up system if you think about it, right? The goal is not to advance. Okay, so we're not like that over here. And it's good if you go to industry, it's good to think about these things as well, right? What is my goal in industry, right? Is it really to satisfy the shareholders so that we can make speculative money? Or is it really to deliver a product that's useful for people? Right? And there are two different approaches over here. And a lot of the unfortunate approaches are in the shareholder part, as opposed to true products that can actually be useful for humanity and people, right? Okay, maybe I'm talking too much right now because I'm in flight 57, but hopefully this gives you a mindset of what we have here. So openness, collaboration, hard work, and creativity. That's what this course will be kind of about also. But these are some of the principles that we follow in my research group too. So I strongly believe that if you do quality work, this defines your impact. I'm very worried that this will change in years that are to come because of AI and all this mess that really dilutes the quality. But I think over time, this quality is going to be a lot more important than, let's say, not so high quality things. I have this example from my own research. I think we always strive for quality research. And in the end, even though people may not buy it early on, over time, they come to see the quality and they come to, I'm going to give you some examples also from my own experience. But I think with a lot of AI doing a lot of things and obfuscating things, I don't know what will happen, right? For example, you probably have seen the Studio Ghibli. These are things that are amazing things that Miyazaki drew. I watched a lot of his animes, and people plagiarized all of that, right? And there is no consequence at this point for that sort of plagiarism. This is no question about it. It's called plagiarism. How do you handle that, right? This is actually a real concern, I think. Somebody did extremely high quality work in the 1980s, 90s. He still does high quality work. And now somebody plagiarized it, and yes, he's had a lot of impact because somebody plagiarized it, but does he get the, maybe credit is not the right word, but recognition that's needed? Or is it stealing, theft? How do you handle this, right? These are, I think, very important ethical issues. This is not an AI ethics course. And I hope some people are covering this in AI ethics courses because this is going to be extremely important. But it has very broad implications on everything we do, including how we design computers, actually, and including how we do research in the end. Okay. Okay, so my suggestions to you is not stay away from the fundamentals. There's a lot of hype today. Your company may be asking you to plagiarize XYZ. Don't do it. Follow your passion. Don't get derailed by people who don't believe in things, assuming you're doing a good thing, of course. Find a good medium where you actually can innovate and do good work. And I think a lot of the time you may be passionate about something, but you need to learn. You need to actually build a lot of infrastructure to enable that. I'm going to give you some examples from my own, our own research over here, but you may apply this to other things as well. And this requires hard work also. So kind of this course is going to be hard work as well. So you can think about it that way. And I think resilience and focus is really important in making things happen. And I strongly believe that, especially in computing platform design, but also many things. If you have an idea, and if you want to make it happen, you got to be really focused, right? Because if you have a really new idea, truly new idea that not many people have thought about, immediate reaction will be, that idea is not good. Many people have gone through this, right? And immediate reaction would be to destroy that idea, potentially destroy you together with the idea. So you got to be really resilient and tough and focused to make it happen. But to do that, you need to work hard. To do that, you need to build infrastructure to demonstrate things, right? And in order to be able to do all of that, you have to be passionate about something. Because if you don't care, you're not going to do any of that, right? You can develop the biggest idea in the world and you don't care and move on to something else, right? That's how it works. That's why passion is extremely important. Okay. But I think in the end, learning and scholarship are the pillars of what enables new ideas and make them happen. Okay, I think I've already said this. So in the end, I think you can certainly make a good impact on the world if you focus on the right thing with the right mindset. And again, I will go back to Aristotle over here. Okay, I'm going to take a break soon, but you can watch some of these interviews. And I think a lot of the things that I just said feed into this interview that was just published 2 days ago. If you're interested, I would recommend reading that interview because I spent a lot of time on it. And you can take a look and see from a limited perspective of robust system design, some of our experiences. And hopefully it'll inspire you. Okay, maybe I'll cover Hamming and then we can take a break. So this is one of our required readings because it's not just me. Again, there are a lot of smart people who have walked this earth. Richard Hamming is one of them. How many people know the name Hamming? Okay, that's good. Where did you learn about Hamming? Say it again. Codes, yeah, Hamming codes. Yes, yes, error correcting codes, right? He actually essentially was the, let's say, forefather of the error correcting code, control code systems. And a lot of the error correcting codes have his notion of Hamming distance incorporated in it. How many people know about Hamming distance? Okay, how many people do not know about Hamming distance? Okay, that's good. I'll give you the idea basically. Hamming distance is basically if you have two equal length strings, the number of characters in which those two equal length strings differ. Okay, so I have ham, H-A-M, and then jam. Those are equal length strings. Three, each have 3 characters. The Hamming distance is 1, right? They're different in the first thing. I have ham and ham. Hamming distance is 0, right? Ham and hat, Hamming distance is again 1, right? Ham and Hamming, well, no Hamming distance because these are not equal length. Then you have to go to some other concept, for example, edit distance. Edit distance was introduced on top of, not exactly on top of Hamming distance, but edit distance is actually when you have non-equal length strings that you need to compare. Here, it's called edit distance because you can think of one of the strings to be edited, right? It actually was edited. So there could be an insertion in one string that doesn't appear in the other string. There could be a deletion. There could be a mismatch. When you have Hamming distance, all you have is mismatches because you have equal length strings. There's no concept of insertion or deletion of a character. Okay. And edit distance is going to be very important when we talk about genomics because a lot of the genomics is based on comparing texts, DNA strings, let's say, and they're not necessarily of equal length. So hopefully this gives you an idea of, so it's good. It's very important to know the fundamental concepts because they could be very useful. Then the question becomes, how do you compute Hamming distance efficiently, right? Now you can think about hardware, right? We're talking about an algorithm. You can have algorithms to compute Hamming distance. Think about how do you, there's an algorithmic aspect of computing Hamming distance. Hamming distance is easy compared to edit distance. How do you compute Hamming distance of 2 strings, 2 arbitrary strings? You need to somehow know the alphabet, for example, to be able to do that. At least everything could be a bit string. And then you compare every single bit, right? You can do an XOR of, you can represent the first bit string as a string of bits, the second string as a string of bits. They should be equal length. And then you can do an XOR of bits, bitwise XOR. And if the bitwise XOR has any ones in it, that means they're different from each other at that particular position. If that bitwise OR doesn't have any ones, they're all zeros, then that is a Hamming distance of 0. But now an XOR is not enough, as you can see, right? You have 2-bit strings, and you have represented them, and then you did an XOR. Now you need to check how many ones are there, right? Because that ones, the number of ones after you do the bitwise XOR is the Hamming distance. Not exactly. That's at the bit level. If you want to do it at the character level, you need to convert that to the characters. Okay? So it's good to think about this, right? I just gave you a very simple example of Hamming distance. And you can design algorithms, bitwise algorithms, and then you can design the hardware. Assume that you design that bitwise algorithm. How do you actually do the hardware to do this? You can do all of those in parallel. And then how do you actually count the number of ones in the resulting bit string? So we're going to see some bitwise execution models in memory soon that actually match this. But if you go to edit distance, it's going to be much harder to both develop algorithms as well as to develop accelerators potentially or computation methods to compute the edit distance. And there is a lot of work on how to compute the edit distance efficiently at the algorithm level, and also how to accelerate it at the hardware level, and also how to co-design the two things. Because some algorithms that you develop to compute the edit distance may not be a good match for today's hardware. Again, people develop algorithms. They have a new idea. They have a great idea. They implement in today's hardware. It sucks. It's slower than the stupid algorithm. Why? Because today's hardware is not a good match. You need to design some other hardware to actually accelerate this thing. And then it actually is fast. So it's good to think about these. Someone may have a great idea at the algorithm level. They may actually be thinking big, but that algorithm may not be useful for today. That algorithm may be useful for a memory-centric hardware, for example, like we will talk about later on, 20 years down the road, 5 years down the road. Again, it's good to think about this bigger perspective, right? If your goal is to accelerate something in today's hardware, you need to constrain yourself to what works well in existing hardware, right? And that's very constraining in that sense. There are, of course, benefits to doing that. You can sell better systems that way immediately, potentially. But if you are thinking about the long term, that may not be the right thing to do, right? Okay, I'm going to stop here. Let's take a break for how long? Maybe until 2:25, 2:26, and then we'll continue. And maybe we can fix this problem in the meantime. Yeah, I don't know why it's okay, sure. Yeah.
Just to make sure.
Yeah, the pointer.
You know?
So here we go. Test, test.
Hello? Should we increase the volume? Hello?
Volume
It's
is
okay.
It's changing now.
Yeah, it's, I can hear, but it's very thin.
It's very low, but maybe it's the noise.
it's because of the noise.
No, but it should not capture the noise.
Go to, is that Zoom? Go to
Yeah.
settings. Q. Audio. Test. Microphone. Speak into the microphone.
Hello?
More.
Hello, 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 hello.
Thing is wrong, and we fix
You
that
redirect
tomorrow.
it.
Is
Yeah.
the labeling.
Good. Thank you so much.
Thanks.
I think, yeah, it's good now. Yeah,
Okay, is it good? Okay, the broken microphone is fixed now. That's good. One robustness issue solved. But if this was a safety critical situation, I don't know. Maybe it would have been, it would be too late. Okay, it's good to think about it that way. Okay, I think I've talked enough about Hamming. I'm going to get back to this soon, give you some specific paragraphs, but Hamming has some very good advice on how to think about the world and how to do research, how to do leading research. And I think he's a good person to hear at the very least. I agree with a lot of things he describes in this transcript of his talk that he gave at Bell Labs. He spent almost his entire career at Bell Labs, which used to be a prime research institution. Not as much anymore, unfortunately. All good things come to an end, or they degrade, but hopefully new good things start afterwards. But essentially, he gave this maybe around the time of his retirement to motivate and inspire people who are doing research at Bell Labs and describe his experiences on how to be a good researcher. Okay, I'm going to get back to this, but I think why am I telling you a lot of this? Because I would like to set your mindset to be at the right place for this course, right? Again, if your mindset is expecting we go through how exactly a processor is designed, it won't be a formative experience for you. This was one of the comments that we received for students who actually had the right mindset, let's say, when they took this course. They thought this was a formative experience. But if the goal, the course goals are not really aligned with what you expect to learn, that may not be a formative experience. And I cannot guarantee it would be a formative experience in that case, because I think teaching is not a one-way thing, right? I can do my best, but if you're not aligned at some level, then it may not work out well. Okay, so high investment, high return. I think the course is a lot of work, no question about that, but you will learn a lot also in the end. And our grading is not harsh, frankly. And hopefully you're not here for the grades, right? I teach this digital design and computer architecture course. It's a lot of work, no question about that. In the end, almost 83% of the students pass. This is much higher than many other courses that are given in the first year at ETH. So it's good to think about it that way, right? My goal is for you to learn. So that's why we provide a lot of opportunities to learn, think, read, etc. But passing is not that hard, in my opinion, in the grand scheme of things. And hopefully your goal is not just getting the best grades, right? Because in the end, again, a bigger perspective, 10 years down the road, nobody will care about your grades. Right? Everybody will care about what you have done, right? If you're in research, for example, if you're in academia, nobody cares about any of your grades. I tell my PhD students, take courses, get the best out of them, just pass them. You don't need to be the best in the class. Basically, don't put the extra effort to something that really matters, right? Of course, learning sometimes, if you learn really well, you also get the best grades, right? But sometimes you learn a lot without getting the best grade also. And that's my experience with academia. Again, that's a critical view of academia, if you think about it, right? Academics tend to think our grading systems are the best. They actually pick the best students ever. So if a student actually gets the highest grade, that's the best thing. But I think that's not correct in general. It's good to think about that. Okay? Now, if you're consistently getting the best grade in everything, that says something, no question about that. But if you're actually, also, if you're consistently getting the worst grade in all of the topics, that also says something probably. But if you're somewhere in the middle, that may be normal, right? There are topics that you like, there are topics that you don't like, there are things that match your style, there are things that don't match your style. So it's good to think about what you learn in the end, right? Because in the end, that's what really matters, what enables you to do bigger things. Okay, we record all the lectures. I would suggest still attending class because I think classes are good to attend. You can interact, you can ask questions if you want. Feel free to ask questions anytime, but also you can do this on your own. Yeah, YouTube allows me to watch lectures on my TV while drinking beer. Yeah. Okay, yeah, we actually are very responsive, but you got to ask questions and make remarks. So if you find something that's wrong, for example, in the whatever part of the course, in the lab, in the slides, in the papers, bring it to us. Don't wait until the course ends and then write a comment in the teaching evaluation saying that there were wrong things in the slides or in the whatever. I think the exact comment was there was something wrong in one of the assignments. How can I help at that point, right? I cannot, sorry. It's not even clear to me what is wrong, right? And essentially, it's a useless comment. That comment is useless, sorry. This is like some of the comments that reviewers make sometimes. This idea is not good or whatever. Give me a useful comment, right? If you think something is wrong, okay, we're happy to correct it. We do it in the scientific domain. Why wouldn't we do it in the educational domain, right? So please tell us, right? This is really important. Okay. Okay, I'm going to skip this. Yeah, I think the course is actually relatively easy because we have homework, labs, and lectures. And you're going to see more of this course thing soon. In lectures, we cover a lot of things. Not all of the things that we cover are subject in the homeworks. And certainly labs, we cannot do a whole lot because there's limited time. So labs are actually an even smaller fraction than what we can cover in lectures. So lectures are here to motivate you, give you ideas, give you insights, enable you to think about different things with different trade-offs. Homeworks are there to exercise, let's say more concretely, some things. And labs are there to actually, for you to do some implementation that is not otherwise possible in lectures or homeworks. So these have different components. And then in the end, there's an exam. And that exam is usually, if you look at past exams, there are similar concepts that we ask about. But again, it won't be exactly the same questions, right? Sometimes when I give the DDCA, Digital Design and Computer Architecture, and hopefully this course is different because you guys are master's students, not freshmen. Somehow some DDCA freshman students expect exactly the same questions like last year. Is that a reasonable expectation? How many times do you encounter real world problems if you're an engineer, let's say, if you're a computer scientist, and you're trying to solve a problem in the field, and you know the answer because you solved it yesterday, or the previous day, or the previous day, or the previous day? A very small fraction. You'll need to apply the concept. You'll need to apply the thinking, right? Why do people expect this from exams, right? You need to think in an exam. And that's a good exam if it enables you to think, right? Because in the end, I don't want my airplane control system designer to mess up because they weren't given exactly how this airplane should operate. They need to think how to make it work, right? So that's why. So you cannot just memorize the questions and spit them out because the real world doesn't work that way. And again, this is DDCA. in computer architecture, we're master's level. So hopefully people are more mature. Okay. Okay, there are a lot of paper reviews that we will assign. I think you learn a lot this way. Some of them are required, and there are a lot of possibility to gain extra credit in this course. So you can actually read a lot of papers, critically analyze them, and you can get a lot of extra credit. Even if you don't do great maybe you're not a great exam taker, for example, right? You come into the exam and first half of the exam, you spend panicking. And then the second quarter of the exam, you barely start understanding the questions. And the last quarter you solve, but it's too late. And this happens. I mean, not everybody is an exam taker in the world. So you can know yourself and spend the effort on doing more reviews, for example, right? So it's good to think about it. I'm giving you kind of strategies of knowing yourself also. Right? So if you're not a great exam taker, I understand that, right? And the academic system is designed for exams, but that's not necessarily a good system for everyone in the world. Okay, so it's good to think about this. But in the end, I think what matters is learning. I think what I really care about is hopefully you'll learn a lot from this course, and hopefully your mindset will change in a good way. Okay, these are some of the good comments. Okay, so I think well, I approach this course as a learning experience. So try to learn as best as possible and think about long-term trade-off analysis, right? Our goal is to really think about concepts in a very fundamental way, even though the concept may be very new itself. It may be introduced like 5 days ago. What is the fundamental thing about this concept, right? How can it affect things into the future? How is its scaling characteristics? 10 years down the road, how will it evolve, etc.? It's good to think about that, basically. So more than anything else, it's good to think critically in this course and use this as a way of improving your decision-making skills. So yeah, basically, these are the things that we're going to cover a lot. Concepts and ideas, fundamentals and cutting edge. And I think these are actually very much related. You may be covering a cutting edge concept that someone introduced yesterday, but in a very fundamental way. And the concept may be in a very fundamental topic as well. And you're going to do a lot of hands-on learning with exercises or labs and homeworks. But again, I will emphasize your mindset will determine what you get out of this course, right? So it's good to set your mindset or say, okay, this course is not for me. Okay, so I think that's why I also put this reading, because this reading is more about mindset than anything else. I will give you some examples here. This was Hamming, by the way, with his cat. He was a hard-headed researcher, no question about that, which is fine. But he says, let's read it, I guess. If you really want to be a first-class scientist, and I would probably generalize this, first-class human, you need to know yourself, your weaknesses, your strengths, and your bad faults, like my egotism, right? He's critically analyzing himself over here. How can you convert a fault to an asset? How can you convert a situation where you haven't got enough manpower to move in into a direction, when that's exactly what you need to do? I say again that I've seen, as I studied the history, the successful scientists change the viewpoint, and what was a defect became an asset. So how do you make the defects assets? It's good to think about that, right? I like this also, basically, because I think this is actually important. And he's very critical, as you can see. This is in this transcript. I claim that some of the reasons why so many people who have greatness within their grasp, they have a lot of good things, basically, but they don't succeed are they don't work on important problems. That's basically, I think, really important. What is an important problem? It's good to think about that. There should be a taste over here. He also says they don't become emotionally involved. That's the passion part, right? They don't try and change what is difficult to some other situation, which is easily done, but it's still important. Basically, they do not adapt, let's say. If you're not flexible, it may not work also. And they keep giving themselves alibis why they don't. Basically, they keep finding reasons to not be flexible, let's say. They keep saying that it's a matter of luck, meaning to do something great, you have to be lucky. But I think, yeah, it's good to, in this luck, yeah, I'm not going to go read more over here because the rest requires you to actually read the rest of the thing. But this luck is important, right? Yes, certainly people get lucky, no question about that. But you can bias the luck, right? Louis Pasteur said, chance favors a prepared mind. Right? This is a great quote, actually. If you want to be lucky, get prepared. Because you may actually have the potential to be lucky, but you may not, if you're not prepared, you cannot innovate in a good way, right? Because you don't know what to do. You may, for example, find some, let's say, some new phenomenon in a device that you're examining, and you may not even see it. Right? All the data is there, but if you don't know how to analyze the data, if you're not prepared, if you don't know what to look for, you will not be able to make that discovery. Right? But if you actually spent hours and hours and hours, years and years and years to educate yourself, to understand how to do the data analysis correctly, to understand what to look for, to read papers that have done the right things to actually discover big things and learn from them, to figure out what to do, what to look for, then all of that data may enable you to become lucky and figure out that big thing, right? So this is actually how chance favors a prepared mind. You actually invested enough time and effort to become lucky. Otherwise, you may not even get lucky. So that's the idea, basically. That's what that quote means, in my opinion. Chance favors a prepared mind. But no question about that. There's some amount of chance also involved. So you can do all the right things, but you may not be able to discover something new necessarily, because there's some amount of chance. Okay. Okay, so I think this reminder, I've already said this is not a basic computer architecture course. Take DDCA and FOCA if you're looking for a basic course. We're happy to have you next semester. I don't know if I'll teach both courses because it's a disaster to teach 2 courses. I think it's a lot of work. Do you think we should offer FOCA again? Do you think we should offer FOCA again? Very much so, okay. Yeah. Yeah, I think it fills a gap, but again, I enjoy teaching, but teaching 2 courses is not easy, let's say. And I respect people who can teach 4 courses and still be passionate about it. It's not easy, I think. Okay, but basically this course covers advanced topics building on basics. However, the topics are very fundamental and very relevant to the real world. So for example, we'll start with memory and storage systems. We'll cover a lot of issues there in depth. And this is the major bottleneck in today's systems, memory and storage. Computation is not that important. Sorry, people working on computation, you're working on important things, but not that important. More people should be working on memory and storage. We'll also talk about parallelism, multiprocessors, bottlenecks, interconnects. We're going to cover many issues in depth, coherence, consistency, etc. later on, but that comes later on. And we'll cover many cutting-edge research topics spanning across the computing stack, like robustness, efficiency, handling data movement. We'll talk about simulation and modeling, how to do it, let's say, correctly, technology scaling issues. So there's a lot we will cover, no question about that. But if we were covering the basics, we wouldn't be able to cover them. And if we were covering the basics, it would be yet another DDCA or FOCA course. Makes sense, right? I haven't figured out how to replicate myself so that I can do actually many courses concurrently. That's parallelism. People are working on it, hopefully. Not me. Okay, so these are the courses. I've already shown you these, but just as a reminder. Okay, any questions so far? We're going to cover more course logistics tomorrow about like specifics of what assignments are assigned first week, where to upload them, etc. But I'm going to go into some basics of computer architecture and where we stand today before we go into course logistics more. No questions? Feel free to ask questions. Again, your questions also will enable you to get more out of this course, right? I can tell you what is in my mind, but maybe you have something else in your mind that enables something bigger in my mind, right? That's how brainstorming and interaction works. Okay, so why do we study computer architecture? Essentially, we want to enable better future computing platforms, hopefully. Why do we do computing is actually the real question. You may have seen these slides in some of the earlier lectures if you've taken. I'm going to cover some of the basics first, and then we're going to jump into more advanced things. So why do we do computing is the key question. Anybody? Why do we do computing? Do what? Okay, I see that's one answer. Solve problems, basically. You're solving your not doing math problem. So yeah, if you generalize that answer, I would say, I want to solve problems. His problem is math. He wants to solve it by doing computing. My problem is, when I think of something, it should appear to you also as an image so that you can also see it. Hopefully computers will do that, right? That's a problem, basically. That's a very concrete problem specification, right? So we really do computing to solve problems. There are many problems that we have, and our problems keep increasing, accumulating, right? And humans are great at creating more problems. Even though we have so many resources, we like creating more and more problems. Some of the problems are very fundamental, some of the problems are very human generated, but basically there are a lot of problems. So if you reword this answer, even if you may not be able to completely solve a problem, at least you should gain insight into how to potentially solve a problem, because a computing system may not be able to solve it completely for you, right? But it can give you some insight based on some data analysis or whatever. Here's something to look at, right? It aids you, basically. It's an augmenter as opposed to complete problem solver. And this is what Hamming had in mind, basically. Hamming wrote a lot of papers and books, and one of the things he said was, computing is not about numbers, it's about insight in the end. Yes, computing can crunch numbers, but in the end, what insight do you get out of those numbers, right? That's the purpose of math also at some point, right? Okay, or if you extend the answer to enable a better life and future, hopefully. But technology is agnostic of your goals. So some people's goal may be to enable a terrible life and future for most of the world. It's good to think about that also, right? This is where ethics also comes in, but technology can be used for good or bad, and good or bad, definitions of good or bad actually differ in terms of the morality perspective of people have. And morality is very, let's say, normative. It's not really, there's no absolute over there in general. But let's think positively. Okay, so how does a computer solve problems? This goes back to us working with electrons, at least in today's technologies. Today's technologies are all electron-based. There's maybe some other technologies that are something else potentially based, but we're going to look at electrons. And the next question is, of course, how do you get a problem to be solved by electrons? And this brings us to the transformation hierarchy that I already introduced at some level, right? You have a problem, and you want it to be solved by electrons. Unfortunately, we cannot communicate directly, as we discussed earlier. So we translate the problem to an algorithm, and then write it in some language, and then execute on some system software, and execute the program using machine instructions, compile it down to machine instructions, which is the hardware-software interface. And then those instructions get implemented in a microarchitecture, which is implemented using logic gates, which is implemented using devices, which operate based on the principles of electrons, essentially. And we cover a lot of this, essentially, in the DDCA lectures, a little bit in FOCA also. Okay. And also some other classes you've taken, for example, talk about algorithms, right? How to optimize them. We're going to take a critical view of algorithms also going into the future. How many people have taken a theory of algorithms course, algorithmic complexity theory? It may be called something else, computation theory. How many people know about the big O notation? Okay, that's good. Where did you learn about that? Anybody? Which course? Computational thinking. Okay, they renamed the course maybe. Okay, fine. Computational thinking. Is that true for others also? Maybe it's a different course. What is the course? Big O notation. Okay, I see. I guess it could be taught on different places. But in the end, big O notation is an example of how to quantify the complexity or cost of an algorithm, right? You count the number of operations at an order of magnitude level. We're going to take a critical approach to that also and say that maybe it doesn't matter. Right? Maybe that's not the important thing to optimize for, because maybe those things are not as costly. Maybe something else is much more costly. Right? So that's what I would like you to get out of this course, essentially. Maybe you learned a lot so far in your career. It's good to think about it as, okay, I've learned these things. Are they true? Or can we do better, essentially, than what I've learned? So it's good to take that critical approach. I keep learning many new things, and I always ask this question. Like, can I do better? Or is this correct? Is this correct today? When was this correct? Was this correct ever? It's always good to ask these questions, right? That is the critical thinking, basically. Otherwise, you take everything and it's the same. Well, you basically believe everything, and you'll be in the mess that we are in today, kind of. That's disinformation age, right? Misinformation age. Okay, so it's that critical thinking is really important, basically. So we're going to critically think about the algorithmic complexity theory also, given what I'm going to describe today and tomorrow. Okay, and we're going to take an expanded view. That's another example, expanded view, right? Your algorithms are designed. It's designed for some worldview in mind, some execution model in mind. Even the theory is there with some execution model in mind. But is that the right execution model? Or can you actually come up with a better theory that fits the quantification, that quantifies the complexity or the cost of an algorithm versus another much better? Okay. Okay, so let me get to the basics. Probably you've seen some sort of definition of computer architecture, but computer architecture is really the science and art of designing computing platforms. And again, this is the broader definition. It's not just a narrow definition over here. It's an expanded definition. It's really how you design the hardware, how you design the interface to the software, how you design the software, system software, and programming model. And I say science, clearly there's a lot of science and engineering that goes into it, but it's also art. And this is actually, this makes a lot of the computer scientists nervous, right? How can this be art, right? Well, a lot of what we do in computer science is actually needs to be art because you don't know, you cannot model everything, right? You don't know how a user will use a computer 10 years down the road. Right? It's good to think about that, basically. Okay, and the goal is to achieve a set of design goals, basically. So you design a computing platform. Your goal may be design a supercomputer or AI supercomputer these days, people call it. To get the highest performance on Earth on workloads X, Y, Z. X may be LLMs. Y may be some nuclear simulations. Z may be something else, right? Pick your own workload. So that's a very different design goal compared to, let me switch to the last one over here, getting the best average performance across all known workloads or all workloads that you want to target at the best performance cost ratio. That's kind of the design of this platform over here, right? Maybe all is too strong, but workloads that you target, essentially. Here, this platform doesn't want to do anything the best because it's designed for the average user. And average user has many different types of programs, right? So it's good to think about that. And the middle one over here is something else. So the design goal over here is to get the longest battery life at a form factor that fits in your pocket with cost less than some dollar Swiss francs. Some amount, basically, right? And you can put performance in there also. So clearly there are some metrics over here, but that's more of a mobile system, like a cell phone in my pocket. In the end, these actually enable a lot of different design decisions. But in the end, designing a supercomputer is different from designing a smartphone, but many fundamental principles are similar. In fact, if you look at the design of a supercomputer today, it's very similar to the design of a smartphone, except some things are slightly different, I would say. Maybe supercomputer designers will hate me for what I just said, because they do a lot of tricks, no question about that. But if you look at the smartphone, you have something in there that's actually a much worse metric, which is energy, right? And a lot of supercomputer designers kind of ignore that, mostly, right? So it's good to think about that way. A lot of the principles we use are actually today similar. You just need to achieve a trade-off that's good. So I'm not saying that designing a supercomputer is harder or designing a smartphone is harder. If your goals are really stringent, they're all equally hard in my opinion, right? And I worked with a lot of people who actually design, a lot of companies also, who actually design these smartphones and also general purpose computers and partially the high-end systems, acceleration systems. In the end, you need to make decisions, design decisions and trade-offs to actually satisfy some goals, right? And fundamental principles are really important. Okay, so I'll give you some pictures of these things. Different platforms have different goals, but this is a computing system also. And there are going to be more and more of these computing systems into the future, hopefully used for good purposes. Unfortunately, humans are bad. This is another computing system, Mr. Bean. Do you know? How many people know about Mr. Bean here? Okay, that's good. You guys are not that young. Sorry. Or Mr. Bean is still popular? Is that maybe that's the okay? I didn't know. I haven't watched Mr. Bean for many years, but I like this picture. So have you seen this episode? Yeah. Okay. Some people have seen. Okay. In this episode, Mr. Bean is driving a self-driving car, as you can see, and it may be a more reliable self-driving car than relying on a computer. Okay. Anyway, that's a joke. But he has envisioned self-driving cars, as you can see. But this is another self-driving car. You can see the computing infrastructure that went into it. There are many different platforms. Genome analysis platforms may become like this. This is an example system in your pocket. I like using this picture because it shows that this thing is a processor, right? It has a lot of computation units and caches. Actually, most of it is SRAM in the end. But the rest is darkness. Now, why is it darkness? Because it cannot do any computation. Right? So there's main memory, which we're going to talk a lot about. There's storage, there's sensors, and all of those places should be enabled to do computation, as we will see in detail with many techniques in this course. Okay, this is another example. This is a data center. This is a supercomputer, which looks similar, but they're optimized in a very different way, right? Data centers optimized for more, okay, I don't want to call it necessarily general purpose. At least a cloud computing data center is for general purpose workloads, right? Anyone can submit jobs. but a supercomputer is optimized for specific workloads in general. And the cost requirements of this is much more stringent than the cost requirements of a supercomputer in general. Yeah. Okay, it's another supercomputer, and I cannot keep up with those. This is Google's TPU, tensor processing unit. Essentially, it's a systolic array engine where this is the core of it. You have a matrix multiplication that's done as the inputs to the matrix flow, and they get multiplied in this array with the weights that they need to be multiplied with. And in the end, you get a product of matrix multiplication. That's the idea. So it's a systolic data flow. Basically, you send the inputs this way, and there are multiplication and accumulation units over here internally, and the data elements get multiplied with every single weight that are in the matrix. So you can store your matrix over here, or at least the weight matrix, and the input matrix can be actually streamed in using data flow. This is a systolic architecture. That's fundamental principles were developed in the 1970s. This topic was kind of, I don't want to call it ignored, but did not really have a whole lot of impact until people started doing machine learning, which is really a lot of matrix multiplications. But it's such a fundamental concept. I was covering systolic arrays as early as 2010 when I started teaching at Carnegie Mellon. And people would ask me, why are you covering systolic arrays? Nobody built systolic arrays. And the answer I gave them, this is such a fundamental concept. It is useful, and it's going to be used. I don't know where it will be used, but it's going to be used. And it doesn't matter if it's not going to be used in my lifetime. It's such an important concept that it has to be covered. It's a different way of doing computation. So that's our goal in this course. It may not be used today, and it may be developed in the 1960s, and this was the case in 1970s, but it's good to understand the beauty of the ideas sometimes, even if no one uses them, right? I think that's really core of being very fundamental, in my opinion. Again, I will go back to Aristotle probably here, but we really need to go back to that, basically. Not everything has to have an application immediately. Not everything has to have an application 5 years down the road. Not everything has to have an application 20 years down the road. You should not be able to imagine the applications in some cases, right? But you should be able to have the background and the artistic and scientific viewpoint to appreciate the concept and to see the potential in it. I think that's what's missing in a lot of what we do today in the world and the universities. We're very application oriented. It has to accelerate the LLM of today. I don't care, maybe, right? LLM of today maybe is fundamentally limited in some things, right? I should be maybe thinking, what should I be doing so that I can enable the next big LLM that can actually do something that is not possible with LLMs today? And that requires fundamentally different hardware. Right? So that's the thinking we need to have. Right? That's why you're not going to get out of this course what is done today and how should we tweak it. This is a good example because I was teaching the systolic array concept for many years before this got actually implemented. And I'm not the only one, clearly, but I was one of the people in the minority in the computer architecture community who was teaching these concepts. These days, everybody's teaching systolic arrays because Google has implemented it, right? That's why we're going to talk about memory-centric computing, even though there are not many examples of memory-centric computers today, but there is a fundamental value in the concept. And I believe actually 10 years down the road, 20 years down the road, 30 years down the road, hopefully sooner, we will get those memory-centric computers and that will enable maybe the next, I don't want to call it the machine learning revolutions, but something better, let's say. Because I think today's machine learning models and AI is very limited to how we can do computation with GPUs, for example, or this. Even this is old today. Right? Okay, so Google has improved TPU, mainly the memory system, in many different ways. So this is happening today. But you can see that this platform, okay, I kind of digressed in an important way, but this platform over here is a specialized platform, right? It's very different. Its goal is to be very, very specialized. In a sense, it's very similar to the supercomputer, right? The supercomputer is designed for, I don't know, doing nuclear simulations, molecular dynamics, etc. That's the traditional HPC, high performance computing workloads, scientific simulations, building nuclear bombs. Again. Technology is agnostic to morality. But this is doing matrix multiplications much faster, right? So it's even more specialized. And you can build, using these components, an AI supercomputer also. And that's what many people do today, actually, including Tesla. This is Tesla's chips that are used in the field for inference. They actually do a lot of matrix multiplication again to calculate essentially what to do, what should the self-driving car do. I don't know if it does well. I don't think so. I wouldn't trust it. But people are trying, let's say. I would trust maybe some other companies' products better. Anyway, the good thing is they're designing chips. And the goal is, again, to do matrix multiplications as fast as possible. Okay, I'm going to skip some of these things. Maybe we'll get back to it later on. But they're also limited by memory. So a lot of these accelerators have a lot of memory, as you can see on them. So we're going to look at memory a lot. But if you think about it, all of these accelerators are, even though they're very specialized in how they do computation, their memories are very primitive. They basically use the memory to get the data, and they write the data back, and then they get the data, write the data back. So there's a lot of data movements that happen. So we're going to look at that problem a lot. And also, this to train these models. So when they run cars all over the place, they get a lot of information, a lot of data. They ship this data to their data center, essentially an AI supercomputer that consists of a lot of these things plus GPUs. So they actually have an AI data center to accelerate machine learning training. So this is what's happening in systems today. People are building chips, specialized chips, and people are building the system on top of that. People are building compute clusters, and people are building the software to do this. So a lot of things are being re-examined today. In this particular case, it could be to serve the purpose of training for self-driving cars, right? And for that, you need to design new hardware, new system, and new software to do compilation, for example. How do you compile a machine learning training software into this new hardware? It's good to think about that. So people are thinking across the stack. So this was the example that I gave you of cross-layer design. So this is happening in industry, and Tesla is one example. Many companies are doing something like this. The chip may be a GPU. Today, a lot of people are using GPUs. There's also another craziness that's going on that is making NVIDIA very rich. Everybody wants to buy GPUs, and nobody wants to feel that they're, let's say, left behind. Of course, the GPUs are very processor-centric. We're going to look at some of those. And the matrix multiplication units is a really small fraction of that GPU. So NVIDIA is very happy because everybody is paying them money, right? People are getting rid of good people who can think differently from companies to buy GPUs. So it's good to think about this mindset, right? Is that a good mindset? I don't know. Just to get another GPU or another GPU cluster, you're getting rid of some people, some person who can actually invent a new algorithm, maybe. Okay, it's good to think about that. Okay, and this is a GPU, right? This is the culprit. Okay, I'm just joking, of course, but there's, as Freud said, every joke has some truth in it. Okay, so these are, GPUs are also interesting because these things were not as popular until people figured out how to use them to train neural networks and also do inference on neural networks. And these days, people are adding new functions to it, like tensor cores, to do things much better. NVIDIA has added dynamic programming algorithm instructions to do essentially edit distance calculation, for example. It helps edit distance. But these are some evolution of GPUs. This is, again, just to give you examples. And there's a lot that goes into the technology in GPUs, including the interconnect technology. These are some interconnect examples that I'm not going to go into over here. But you can read, again, papers about it, which are usually high-level things. Okay, one of the main reasons, as you can see, that there's a big growth in AI models. It's good to take a critical view of this also. Is this the right thing to do? I'm not sure. I don't think so, actually. But it's good for people to be exploring. But exploring is one thing, and going crazy about it is another thing. Okay. But there are actually a lot of things that we will cover in this course that will enable you to design systems better. So this was in 2016, how different GPUs were connected to each other using a hybrid cube mesh technology, using the ME-Link standard. Well, not standard, ME-Link, which is NVIDIA's proprietary interconnects. But if you look at the interconnects, you're actually connecting a cluster of GPUs over here very tightly. And then there's another cluster of GPUs over here. And the connections between these two clusters is actually not so tight. And we're going to cover interconnects, which are really important to cover. And in more recent communication methods, it looks like this. So you can see that to scale up the system, they had to scale up the interconnect. And you can see that there is a set of routers over here, intermediate routers, that enable communication between these set of GPUs and these set of GPUs. So it's good to think about that. Okay. Okay, people are also experimenting with other things. A lot of them are actually driven with machine learning today, which is a good thing and a bad thing at the same time, because machine learning is very specific, but it's driving a lot of innovation in architecture and systems. How many people know about this company? Cerebras. Okay, that's good. Yeah, it's they've designed a chip. Maybe I should go to this picture. That's this big. It's wafer scale, as you can see. That's why it's a wafer. Normally what you do is you get the silicon wafer and you cut it into pieces, and each piece becomes a processor. Now, they didn't cut it into pieces. They basically designed the whole set of processors on top of this entire wafer. And their goal was to actually use all the transistors so that you can do a lot of computation in parallel and a lot of memory, SRAM in particular, static random access memory, close to that computation. And in the end, they have a lot of cores, as you can see, which is a lot. And this is the to compare size. So this is the largest GPU, which is this small, as you can see, right, at the time. So they have a lot of transistors which they can use for many different purposes. And you can see the on-chip memory is 44 gigabytes, which is actually really small if you think about it. 44 gigabytes with very expensive memory because it's SRAM, static random access memory. And 44 gigabytes is really small for many machine learning models. Okay, maybe we're going to get back to this memory because we need more capacity in many of the models, as we will see soon. But it's good. The reason I'm showing you these things is because this is a different way of designing the chip, right? There's a lot that goes into this design. How do you power this huge thing, right? How much power does it need? What is the power delivery infrastructure for this? How do you cool it? We're already having trouble cooling the small GPU, right? It consumes hundreds and hundreds of watts, a single one. This thing actually is much worse, right? So they had to innovate a lot in that domain. How do you handle faults? If part of the chip is faulty, how do you make sure the entire wafer doesn't go away, right? Normally what happens is if you find faults in a chip today, if you cannot fix it for some reason, you throw the chip. If you throw one chip, maybe it's not that bad. If you throw an entire wafer, now it becomes very expensive, right? Your yield reduces greatly. So there are a lot of interesting design issues and infrastructure issues before this, but there are also a lot of interesting, like higher level issues like programming. How do you design the compiler such that you can distribute the work on top of many different processors over here? I didn't tell you which processors they are, but they're essentially SIMD engines, single instruction, multiple data, kind of similar to GPUs in a sense, but they're distributed across the entire wafer. So you need to design a compiler to take advantage of all of that parallelism and minimize the data movement. So there are a lot of interesting issues over here that people are trying to solve today. And again, this is across the stack. And the reason people are experimenting with these things is because we are driven by higher compute efficiency and higher computation performance. And okay, I can bore you with a lot of other pictures. I'm not going to do that. And this is an incomplete list of people or companies who are designing machine learning chips. I believe there's many more to come. And maybe I hope it's not just machine learning as well. I have nothing against machine learning, but I think it's just a very limited domain. I think, in my opinion, machine learning will shape a lot of domains. So it's going to be fundamental to many, many domains. A lot of things will be AI assisted, machine learning assisted, but there are many, many other problems to solve in the world, right? It's going to be still a while until we get an AI that solves all of our problems. Okay, so this is an example, AI chip landscape. You can take a look if you're interested. Okay, there are other things that people are experimenting with. This is actually a less well-known company, probably UpMem. which was based in France. They were recently bought by Qualcomm. But essentially, these folks are more innovative, in my opinion. What they did was they took DRAM chips, and DRAM is the main memory that's used to build main memories of essentially all computers today. And they said, let's put some computation inside the memory chip, as opposed to having a computation chip and memory chip that's separate from each other, which suffers from a lot of data movement and a lot of energy consumption because you need to move data between the memory and the processor. They basically embedded the processors inside each memory chip. So next to each bank, there is a processor. And this is a programmable processor, general purpose processor. It has some limitations, and we do a lot of work in this area together with them, some of it. But this is an innovative idea. This is a more memory-centric thinking, as we will discuss soon. And this is built, this is real. We have 3 of them in my lab at ETH. We've been working with these guys for a long time. If people are interested in programming these things, I'd recommend taking a look at it. We actually have a programming assignment in this course where you would be able to program them. And it's good that we have 3 of them because not many people have these chips right now in the world. Because once they were bought by Qualcomm, Qualcomm got all of their whatever they had, and you're not going to get anything from Qualcomm. Qualcomm may get your hand, but you're not going to get Qualcomm's money. I'm just kidding. I have a lot of friends at Qualcomm, but it tends to be a company that's a bit harder to work with than a startup that's trying to do something big, let's say. Qualcomm was not always like that. Qualcomm, when it was formed, it was a very innovative company, right? All companies, when they become big, they become a little bit different, let's say, to say the least. Okay, these are UPMEM memory modules. You can see some of them, and you can see the numbers. Like this is, you can see that the processors, DPUs, these are DRAM processing units. Inside the DRAM chip, they have very low frequency processors. And the main reason that they're low frequency is because this is the DRAM fabrication process, which is very different from the logic fabrication process. When you do memory, DRAM at least, you store charge in capacitor. That's what your cell is about. So you need to carve or etch these capacitors inside the chip. And that is really what dominates the fabrication. You need to do that in a way that's reliable enough. So your goal is not logic in a sense, right? So it's a very different goal from logic. Logic, you need to etch the transistors, etc., so that you can do computation. Where a capacitor is very different. You need to store charge in it. You need to actually make sure that thing works reliably. So as a result, adding compute elements with logic, like transistors, and on top of that, building gates, is expensive in the DRAM process because the process is not designed for this purpose, the fabrication process. So the logic element that you add over there is big. It's not as small. It cannot be as small as what you could do in a logic process, in an advanced logic process. Also, it's leaky. It leaks a lot. So as a result, you cannot design it to operate at very high frequencies, like 4 gigahertz, 5 gigahertz, 6 gigahertz that we have today. You can see that it's 350 megahertz in the best case. In the next generation that they were going to have, if they were not bought by Qualcomm, they would have been 425 megahertz, or maybe we have some of the 425 megahertz, do we? I don't remember, yeah. Okay, anyway. Okay, so this is a real system basically that you can, and you are going to experiment with in one of the labs in this course. I think this is fascinating because if you took this course, I don't know, 3 years ago or 5 years ago, you wouldn't be able to do that. The system wouldn't be there, right? If you took a similar course when I was doing my, let's say, PhD or bachelor studies, even GPUs were not there at that time. I mean, they were there, but they were embedded in a system and nobody really thought about them, right? Everything was like the superscalar out-of-order execution processors at the time. So this is how the field is evolving. So in a sense, you're lucky to experiment with things like this, but this thing has a lot of limitations also. So it's very important to have a very critical view of everything, including a memory-centric computer like this. Just because it is a memory-centric computer, I'm not going to go and hug it and say, oh, this is the greatest thing ever. Right? Instead, we take a scientific approach. We say, what is good about it? Let's take a look at it scientifically. Right? And we have written a lot of papers on what is good about it, what is bad about it, what can be done well, what cannot be done well. And hopefully people will implement better systems going into the future. Okay, this is one of our papers, experimental analysis of the opmem engine. Rejected from Sigmetrics. Yeah. So even if you write an honest and very good paper and you do everything right, science right, and I believe you did everything right in a lot of these things, you can still get rejected. So what do? You become resilient. And you still publish it at a good place. This paper is read, and the benchmarks that are introduced by this paper is used by many people in the field today, including companies. Yeah. Now, you don't necessarily get your work reviewed by people who have a good mindset, or even reasonable is not easy to expect these days, because sometimes they take your paper, feed it to an LLM, and then the LLM spits out something random. We have also had that. I'm going to give you some examples maybe later on. It's actually a lot of fun to see that, because what happens is basically you get some comments. Some people who are sitting over here, who shall remain nameless, got some comments like that. You get some comments about the paper, it's garbage. But then you have some other comments about some other paper that you didn't submit, because this very smart reviewer forgot to reset their LLM's memory, I assume, right? Do you guys agree? It happens. So what do you do about that, right? You can make the AI as smart as possible, but if humans are not smart, we have a huge problem. Okay, so that's a user error. Okay, okay. So I'm going to skip some of these things, but we have a lot of information, some of which we're going to cover in this course when we talk about memory-centric computing. Okay, there are also things you can do today. Let's see. For example, today you can have FPGAs, and FPGAs are reconfigurable architectures, field programmable gate arrays, which we have covered in DDCA, for example. You have programmed these in DDCA if you've taken DDCA. DDCA is a very special course in that sense. It's a freshman course, and you immediately get to program an FPGA, right? I think it was introduced by very forward-looking people like Nicholas Wirth. How many people know about Nicholas Wirth? Anybody? Okay. Did you work with him? Okay. Okay. How many people know about Pascal language? Okay, that's good. More people. Did you program with it? Okay. But Nicholas Wirth actually was a professor in computer science at ETH. And he was very forward-looking, and he really believed in designing things in a fundamental way. That's why he designed this course that I have been teaching, and we have improved it, I think, on top of what he has done. And I think he is an original thinker in that sense. He designed Pascal so that he could educate people. He designed a bunch of programming languages and systems. So it's good to think about that. Anyway, I digress, but I think these are important digressions, right? If you have forward-looking people, a big place becomes better. If you don't have forward-looking people, then you're in trouble, right? And somebody else will have forward-looking people, and those places will be good. It's good to think about that, I think. Okay, so basically, FPGAs are there, and a lot of people are using them, and you can use them for many different purposes. This is an example from our work that we did with IBM research over here. Gagan, who was my PhD student, led the work. And if you look at what we did very quickly, you can take a very powerful CPU. IBM has this Power 9 CPU, and you can offload some computation to an FPGA board that is essentially reconfigurable programming units. You can customize the computation to the application. In this case, we customized the weather modeling, stencil computations that are in the Cosmo weather model, and some genome analysis computations, which we had developed. It's called Sneaky Snake. It's a fun name. I like that name, actually. I thought nobody would pick it up. I just said Sneaky Snake is better than whatever it was before. But in the end, actually, if you look at the algorithm, it looks like a sneaky snake. Yeah. Okay. Basically, you can customize the hardware to the computation that's inside the algorithm. And you can offload that computation to this reconfigured hardware that has a lot of memory next to it that it can access with high bandwidth. That's what HBM is. We're going to see HBM a lot later on. This is still an overview. I don't expect you to understand everything over here clearly, obviously, right? I'm not giving you a lot of detail over here, but this does just show you that these things exist. And if you actually know how to program them, you get significant performance energy efficiency improvements. So in this work, for example, I don't have the next slide over here, but if you offload some of the key computation, weather modeling, and genome analysis, you can get energy efficiency improvements of 10 to 20x, 10 to 20 times, compared to executing everything in the CPU. Why? Because you're specializing computation, specializing the hardware computation to the algorithm itself. And also, you don't have as much of a memory bottleneck. In the CPU, you don't have high bandwidth access to large amounts of memory. In this HBM-based FPGA board, you have that access. Okay, this is what you can do. Again, our goal is not to restrict ourselves to what we can do today. We want to do things that we cannot do today. Okay, so there's more actually near memory processing. Samsung, which is a major DRAM manufacturer, introduced what's called function-in-memory DRAM. It looks kind of like this. Inside I think some computation blocks. They have some computation blocks, and they can actually do limited operations. You can see that this is floating point add, multiply, multiply and accumulate, multiply and add, essentially to accelerate machine learning. Their goal is to have a specialized logic next to each DRAM bank where you can accelerate machine learning operations. This is very new, 2021. And they wrote papers about it. Unfortunately, we don't have access to it. Not many people in the world have access to it. So we cannot verify their claims, but it's a step in the right direction from my perspective. It would be much nicer if this was open and people actually got to use it. I think they would also get a lot of traction if they actually opened it up, because the ecosystem could develop if they opened it up. But you need to have the right mindset to be that sort of company. Otherwise, you become Samsung. Okay, sorry. I have a lot of friends at Samsung also, but I think they will understand my joke. I'm going to give a lecture actually when we go. Our major conference is going to be in Korea in mid-October, Micro. And I'm going to meet a lot of them. And I'm going to make this joke over there at Samsung also. I think some of them will empathize with it really well. Some of them will be very sour. And the innovative people will empathize with this. Sour people, we don't care much about anyway. Okay, so this is another example. Samsung and Meta together designed this huge thing. It's a board, essentially, you can see. A lot of memory chips over here. In the middle, there is an FPGA. They call it the buffer, but it's really much more than a buffer. It can aggregate data and can do computation on that data. And here, the reason they did this is to accelerate recommendation systems. Basically, when you do something on Facebook, they give you some recommendations to watch something else. That's their goal, right? Worthwhile goal? I don't know, but it's a goal. There could be other worthwhile goals, in my opinion, to accelerate, but at least they're designing a system that's more memory-centric. Okay, SK Hynix, which is another major Korean company, well, DRAM company, and also a Korean company, which they also designed something similar to what Samsung did in a different type of interface. But their goal also was to accelerate machine learning workloads. So in a sense, it's very similar. They're designing memory chips. So you can see the trend. The trend is memory companies as well as computation companies are designing memory chips that can accelerate computation. So there's more information, especially our PIM course, Processing in Memory course. I think the last incarnation was when? Fall 2023, or maybe even earlier. I don't remember. It covers a lot of these accelerators if you're interested. We will not cover a lot of existing things, but the key takeaway is next to each bank, which will become more clear when we get to more detailed lectures, you have an accelerator for machine learning. Okay, so other companies, system companies like Alibaba. How many people know about Alibaba? Okay, because Alibaba can mean different things, but this is a company, Alibaba. Yeah, there was my favorite restaurant in Pittsburgh was called Alibaba. It was my students. We would always get for our group meetings. We would get food from there. It's a Syrian restaurant in Pittsburgh. Syria is also a country. It's part of our world. People may not think that way, but it's part of our world. And Syrian people are very similar to people from everywhere. You know, it's the same. People are the same everywhere. Anyway, but this was a Syrian restaurant, and people would get sick of having food in our group meetings because I would always order from Alibaba. Because it was great food, you know. You pay $5 US and you get this much food, and it's great taste. What else do you want, right? Okay, anyway, this is a different Alibaba. This is the major, let's say, internet company in China. And they have designed a DRAM chip also. And next to each bank, they have some sort of machine learning accelerator again. And again, their goal is to accelerate recommendation systems because they also do a lot of online services plus online merchandise selling, and recommendations are important for them. Okay, and these are real chips that people have designed. They publish papers about it. They publish works. Unfortunately, they're not open to the entire world, or yet, at least. Now, there are also other examples of this. Today, we have something called CXL. How many people heard about CXL? Okay, some people. Okay, some people. Compute Express Link. You don't need to know. Basically, you don't need to know the details. Basically, the idea is you can have a flexible interconnect connected to your CPU, and this interconnect enables you to offload computation somewhere else. That's one of the benefits of CXL. There are many other potential benefits that I'm not going to go into right now, and it's not important, really. The idea is people are looking at these innovative things where you can offload computation on a memory device, for example, on a storage device. And people are writing papers. So this is something that SK Hynix developed recently, where they could offload database computations in what they call a CMS card, which essentially is an FPGA with a lot of memory next to it. Samsung also has something similar, which is a little bit harder to understand and more cryptic, but you can, again, read more about it. So basically, we're at a very interesting point right now where people are experimenting with a lot of things. Some of the things are compute-centric, some of the things are memory-centric, as you can see, processing in memory. This is an area that we will cover a lot in this course. And there's actually many other experimental chips and startups. So this is an area that's really thriving, in my opinion. So it's good to, you guys are taking this course in the right time, I think. You can also critically think about things. Okay, we do a lot of work on genome analysis. There will be part of this course where we will talk about genome analysis acceleration. If you're interested, that's another domain. And I think this is important because we need to develop systems for different domains, right? Today, a lot of people are focusing on machine learning. But if you think about it, maybe that's not the right thing to do, right? If you look at the resources of the world that is being spent on AI, it's very, very biased. But maybe there are other domains that are also very important. So I think we should not lose our fundamental focus going into the future. Okay, I think this is the axiom that I showed you. I showed you a lot of examples where we need to design algorithms to match the hardware. We need to design new hardware, and we need to design algorithms to match new hardware and everything in between. So things are changing a lot today. Any questions? I feel like I've been talking a lot. Yes. Stupid questions are okay. Yeah, we're going to get back to that in Emerging Memory Technologies lecture 16. But okay, that's a yeah. But essentially, in essence, they're the same, right? You're storing data, right? But usually, what people think of when they say storage is something when you power it off, you don't lose the data. Right? It's non-volatile, essentially. So when people say storage, it's a disk, for example, hard disk. When I power it off, the data is still there, and I can still access it whenever I want. I think that's really the fundamental distinction, why things have evolved differently. Whereas if you look at memory, at least computer memory, which is different from human memory. In human memory, there's no distinction between memory and storage, right? We basically call everything memory. There's a long-term memory, there's a short-term memory, there's forgetting, etc. The analogy breaks when you go to computers. But storage is non-volatile, memory is volatile, meaning whenever you plug this off out of power, you lose all the data in memory. Okay, I think that's the fundamental distinction why things have evolved differently. But of course, there are other distinctions. To make things non-volatile, it takes effort, it takes latency, it takes more energy. So the latencies to storage devices have been long. But again, we're going to cover a lot of these things when we get back. But I think you have a very good point, which is, should we think of these things as separate going into the future, right? So I think that's the next question to ask. Maybe not, right? If actually we have a lot of our data inside storage, maybe we should think about the system in a different way and design it a different way. And we're going to talk about that also, but not yet. Okay, yeah. Okay, what else? Any other good questions? That was not a stupid question. That was actually a very good fundamental question, right? Yes. Mm-hmm. Well, possibly, yes. But I think, I mean, systolic principles have been known, have been designed since 1970s, right? In fact, I assigned one of the readings in my DDCA class, H.T. Kung's paper, seminal paper. I think it's there could be more optimizations that people can do, but I think to be fundamentally more efficient, we need to do something else, something different, both architecturally and also technology-wise. And we're going to discuss that. Hopefully, you'll raise that question later, maybe. Yeah. Okay. Okay, what else? Any other questions, thoughts? These questions may make no sense to you at this point. That's okay, especially systolic arrays, since we didn't cover in detail. But now, if it raised your curiosity, you can go and watch some lectures on systolic arrays. And I think there are multiple different ways of thinking about acceleration, right? You have one architecture, let's say it's systolic. Another one, SIMD, single instruction, multiple data, vector processing. Another one is more memory-centric, right? If you could actually take advantage of the parallelism inside the memory, and you can do analog computation, potentially. That could be much more efficient, right? So basically, there are different ways. The third one that I mentioned is perhaps more longer term, but could be fundamentally much more efficient. And it could incorporate some of the systolic principles inside there. But it won't look like the systolic array hardware that Google has designed. Okay, what else? Any other questions? Okay, no questions. Then let me go through what kind of a future do we want also, because this is fun. And then we're going to hopefully end early. Okay, so this is also a good question to ask, right? Basically, what we have studied so far is the different kinds of things, and we want an expanded view. But what are we designing for? How many people know this bridge? It broke. How do you know? Okay, good. Yeah. Okay. Why do you know this bridge? Because it broke? Okay, that's good. Yeah. So you wouldn't know it if it didn't break, right? So you become famous for designing something terrible. I'm just kidding. But so you know it because you didn't see it in the course. You just learned about it. Okay, that's good. How many people saw this in a course? Okay, which course? Ethics, okay, that's interesting. What else? Say it again. Okay, control systems, that's a good one. What else? Civil engineering? You don't remember, okay, fine. See, that's the important part, right? You don't remember what course, but you get the learning. Yeah, ethics is interesting. In what context was it covered in ethics? Okay, okay, that's good. Yeah, that's true. Yeah. And a longer version, I have other bridges, but this is one of the famous bridges that's taught in many courses. How many people walked on this bridge before it broke? Hopefully nobody, because I don't see anyone that old over here. Yeah. Okay. Basically, yes, it broke, and this is the Tacoma Narrows Bridge. I used to live close to there when I was at Microsoft. And I didn't get a chance to go on this bridge because this is what happened to it. It's essentially a bit flip. It's a robustness problem. A modern, I would rename this to a bit flip. It's a robustness problem. And there's actually a lot of analysis of this. This was one of the good examples where there were no fatalities, human fatalities here. And this is another view. But I went through the replacement of this bridge, which has two bridges. Is going next to it, and it hasn't broke yet. It's not a bad place to go, actually. I would recommend, if you're interested in exploring and if you like the nature of the world, that is still pristine and not destroyed by humans, that area of the world is great in that sense. The Olympic National Park is there. It's an amazing place where you could get 4 seasons in one day. That's okay. So another question. How many people saw this thing? Hopefully not many people, unless you took my course, or did you? Yes, you saw it from my course though. How many people saw it before my course? Yes, where did you see it? I'm curious now. Okay, have it on your wall. Why do you have it on your wall? It looks kind of fun. It reminds you how brittle life is, maybe. So these folks are very happy right now, but if they have a bit flip on that rod, they may not be very happy soon, right? So, okay, I think why am I telling you all of this? I think these are some of my favorite examples on how we should approach robustness or security, right? We built infrastructure, and there's no question that this is infrastructure, and this is infrastructure, and some things may happen to it, and we may not anticipate everything that may happen to it, but we should be ready for the unforeseen consequences. So we should design things such that it can tolerate unforeseen consequences, right? This is very general, but I think it's a very good thing to strive for, because we are designing as computer engineers and scientists, especially system designers who design chips and architectures and systems. We're designing systems that people are going to be relying on in many places where they're not tested yet. Like if people want to go to space, for example, and if you want to go with a cutting edge technology, how do you ensure that that thing works over there, right? Deep oceans, another example, similar to space that we don't know enough about. Right? But I mean, even in this area, right? There are a lot of environmental factors that we may not actually take into account when we design our systems. So essentially, we need to take a different approach. So that's another example, my favorite Mr. Bean example that I know is still popular. That's good. Some things don't change. I wonder if AI changed Mr. Bean in some way or plagiarized it. Potentially, right? The question is, can it generate something better? I don't know. Let's see. Basically, we're designing all these platforms, and actually the platforms we're designing or the infrastructure that we're designing is at a scale that is not there before. How many bridges are there in the world? Multiply that by I don't know how many orders of magnitude, then you get the number of computing devices, right? So it's good to think about the scale at which we're going to operate or we're operating on already. And that's going to increase into the future. So basically, robustness is a big issue. And that's why we're going to talk a lot about robustness in this course. And robustness has many aspects: reliability, security, safety, availability. I didn't add all of these. Predictability is part of robustness, depending on how you think about it. So basically, robustness is very important. This is just to set the stage for some metrics and some things that will come about. Another thing that's important: how many people know where this is? Okay, that's a tougher question, right? Could be anywhere. And I frankly don't know. I borrowed this picture because the credit is over there. Yeah, essentially it looks like not a bad place, right? It's a bit boring maybe, but you can live there, fine. Which one do you want, I guess, right? You want that or this? It's like 1940s Pittsburgh. I used to live in Pittsburgh. And I think Pittsburgh has a lot of bad credit because of what happened in its history, because it was a terrible place in terms of breathing, for example, some of the basics because of the industry there. But essentially, the takeaway is, what kind of a future do we want? Do we want a sustainable place, efficient place, where we can breathe in? Or do we want something where we cannot breathe in, right? Hopefully the choice is clear there. But I think we do also want the productivity that comes with some of the things that that came with industry, right? So I think it's good to not give up the high performance aspects. So you want sustainability and energy efficiency, and this is going to become increasingly more important. And I think this is why a lot more younger people should be involved in governance and making decisions, because older people will die by the time this happens. But unfortunately, the world doesn't work that way. Older people want to hold on to their power, and they want to make the decisions. So as young people, rise up, guys. Because older people are not going to see the consequences of their decisions. You guys will see it. our children will see it, and some older people don't care. That's very sad. Okay, anyway, that's another critical thinking dimension for you to think about. Very important, though. Okay, there are many difficult problems that we have today. Climate is clearly one of them, and sustainability has a very close correlation with the problems that we have in climate. Congestion, which looks interesting, as you can see. Intelligence, have we discovered the fundamentals of intelligence, or are we actually dealing with some things that people claim are intelligent? It's good to think about it. And I think what we have today is not even a scratch of the real intelligence that is there in this thing, in my opinion. And many other things potentially, not just this thing. Okay, public health, clearly. How many people did their bachelor's degrees during COVID? Was it fun? No. For whom it was fun? Doing a bachelor's degree during COVID. Say it again. I see, yeah. Hopefully you won't think of it that way for this course, but yeah, I can imagine some courses you want to skip. Yeah, I wanted to skip them when I was a bachelor's student also, but I was quite diligent, so I found other reasons to wake up for these boring 8 a.m. courses. I don't know how. Yeah, I used to sell bagels at the University of Michigan, EECS building, right before the course started. So that I had to be there to sell bagels. And then I attended the course. And then I had my bagel and the coffee for free because I sold them to other people. That was my compensation for doing service to the engineering society over there. Yeah. Okay, yeah, in COVID, you can skip more easily, fine. But yeah, public health is really important, and we need to figure out how to deal with it more as things become potentially worse and worse. That's why genome analysis is very interesting, actually, and this is a difficult problem. And this is something we're going to describe more and more in some of these lectures. Again, I'm skipping a lot of slides, but we do a lot of work in this area. That's a fascinating area for me. And again, everything that we discussed so far applies for genome analysis also. We want efficient hardware to do this very, very efficiently, and we want efficient algorithms to take advantage of it. And we have a lot of papers on this topic. If people are passionate about this topic, we're always looking for people to do great work in this area. And I believe in 10 years down the road, 20 years down the road, some of the fundamentals that are developed in genome analysis are going to be extremely important to use in the field. Okay, there's some beginner reading. So we write a lot of papers on this topic. So why am I telling you all of this? I'm going to skip some of these. But today, it's machine learning. Clearly, there's a huge demand for performance and efficiency in machine learning, right? This is an example from those people who are building wafer scale chips. It's a nice talk from the CTO of that. And this basically shows that memory compute requirements are growing exponentially, but also memory requirements are growing also exponentially in modern neural networks. Okay. So there's a huge demand for performance efficiency. Basically, performance is still important. That's the takeaway. That's why I've shown you all of these things. Performance is still extremely important because our problems are not getting easier, they're getting much harder. And as we delve deeper into these problems, we need to solve them, and we need more performance. But we don't want this performance to come at the cost of huge sustainability and efficiency problems. And unfortunately, today, the entire industry is in a craze. Countries are in a craze. I don't know how this craze can be stopped, but people are essentially building these huge data centers to get this much potential benefit from existing models. And I don't know if I will even be happy enough to call it a benefit. I don't know if it's a benefit, frankly. And these data centers are going to be powered by nuclear power. So it's a bit crazy, right? So people are driven by performance, but it comes at the huge expense of sustainability, efficiency, and robustness of the world, greater world probably. It's good to think about that. And I think going into the future will be a lot more personalized, hopefully, so that we can solve a lot of the health problems, and we can do better at that. And I think genomics plays a big role over here also, like personalized medical technologies. But I think personalization is going to be a lot more in other domains as well, like robotics, right? It'd be nice to have reasonable things like robotics that is actually doing things for us in many different ways, in education, in public health, in whatever, right? We're not there yet, but I think new things, new models, and new hardware can enable it. So our future will be a lot more personalized and private in every aspect of life, in my opinion. Okay. So why am I telling you this? Essentially, with computer architecture, we can enable that future in a much better way. But we need to think differently. Right? This is another definition of computer architecture. It's really the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, and other specific goals. This is a lot, actually. As a computer architect, you're really designing the system. That's why I liken computer architecture to building architecture. Right? You're really building spaces for people to live. How do you actually enable that? All of these actually go into that in buildings as well. So essentially, we want to enable better systems, and this course will hopefully give you some examples of that. And if you enable something fundamentally different, just like, for example, GPUs have enabled some old machine learning algorithms to become more widely adopted. Systolic arrays have done similar things. You can enable new applications and systems as well. Right? But I think for this, we really need to explore the depths of the technology and new technologies. You can enable better solutions to problems. Hopefully, that's our goal. And you can also understand why computers work the way they do. Okay, today is basically, I'm going to finish soon, but today is a very exciting time to study computer architecture because nobody knows the answers to these, let's say. Industry is in a craze to build machine learning supercomputers. Governments are in a craze to do that. I don't know if that's the right thing, but we should probably take a different approach and think about it differently. There are many difficult problems to solve. Clearly, there's huge hunger for data-intensive applications. We're constrained by power, complexity, technology scaling, which we're going to talk about in the next few lectures, memory bottleneck, which we're also going to talk about in the next few lectures, reliability and robustness problems, programming issues. If you think about it, it could be also important. If you cannot program it efficiently, maybe it's not going to run efficiently, right? And security and privacy issues. So there are no clear answers to these problems. So these affect all parts of the computing stack if you don't change the way we design systems. So there are many new demands from the users. There are many new issues at the bottom. We're going to study some of the scaling issues especially. And there are fast-changing demands and personalities over here. Right? Sustainability was not a concern almost 5 years ago, if you think about it, right? Yes, things were getting better, but people didn't think about sustainability. Today, it's still a concern. It's really important. But again, the decision makers don't seem to be caring about it. That's why I gave a call to you guys over here, right? Okay, so clearly there are no clear definitive answers to the problems that we have. So the computing landscape is very different from even 5 years ago, I would say, 10 to 20 years ago. Every component and its interfaces, as well as entire system designs, are being re-examined today. So in a sense, you can reinvent computing today much better than someone could have done 10 to 20 years ago. So certainly, when I actually was studying computing for the first time, like in the 1990s, 2000s, most of the computers were out-of-order superscalar processors. Intel was king. Today, Intel is almost dead. Right? Again, I have a lot of friends at Intel, and I have a lot of friends outside Intel because they had to go out of Intel, let's say. But we are in a very different world, right? Intel was the dominant king. Today, Intel is dead. Okay. Okay, I think I've already said all of this. For the next lecture, we're going to start from here. We're going to cover some more basics, and we're going to go into essentially memory and storage, and especially focus on memory, because this is the major bottleneck. I'm going to give you a lot of data on why this is the major bottleneck and what can we do about it. And then we're going to start developing techniques, some ideas to actually solve that big bottleneck. And maybe you'll come up with some other ideas. So this is also a very good place to potentially think differently. And you can suggest ideas, and I can tell you whether it has been done or not, to the best of my knowledge, of course. Right? I don't know everything in the world. And don't ask ChatGPT because it's terrible at knowing things. And also, it may steal your idea and do something else. Okay, any questions before we part? Okay, going once, twice. Okay, I'll see you tomorrow then. Take care.